Good evening everyone. My name is Pavan. Today I will be presenting my MS work, a variable OSR delta sigma ADC with LSB-First ADC as Quantizer. So outline of my presentation goes like this. I will be starting with introduction followed by literature review. Then I will go to my MS work, that is non-uniform sampling ADC, followed by future work and conclusion. Then we will go through the comments and queries of the examiner. So in real world signals are mostly analog, so to processing them is done through digital. The bridge between these two is ADC. This ADC performance is decided based on its resolution, bandwidth and power consumption. So there are various architectures which are good in different aspects. First architecture is flash ADC. This is mostly preferred for applications where speed is very important. This is mainly due to the comparators which operate in parallel. Due to this, the speed will be very high. But if when we go on increasing the resolution, the comparator count doubles. So that's due to this, the power consumption also will increase, and the increase in resolution will also increase the step size of the decrease the step size of the ADC, due to which after some point there will be necessary to carry with the comparators. All these things will limit the flash ADC resolution to 8 bits. Designing it for more than 8 bits will not be easier. So to go beyond 8 bits, there are other architectures. One of them is SAR ADC. This works on iterative method. This is a single comparator architecture and mostly digital. This can achieve a resolution up to 12 to 14 bits. But again, the resolution of this is limited by DAC nonlinearity and the comparator offset. To go beyond 14-bit resolution, we will be using delta sigma modulator. What happens in this is, it will be using single bit ADC as a quantizer, which is comparator. In this, the in-band noise will be shaped, due to which the noise power will reduce inside the band. That way we can increase the signal to noise ratio. This way we can go beyond 14 bits of resolution. But to increase the SNR in this, we need to increase the OSR. In Nyquist rate ADC, we could have done it only by increasing the resolution. In this case, since it is single bit, we need to increase the OSR to increase the SNR. So then in noise shaping SAR ADC case, we will be using a multi-bit ADC in delta sigma loop, due to which SNR is also dependent on number of bits. So we need not increase, OSR need not be very high to increase the SNR. So when we come to high resolution ADCs, noise shaping SAR ADC is one of the option, because it will do noise shaping at lower frequency. The other option is dual slope ADC. It achieves high resolution using integration based technique. But in dual slope ADC, basically it takes 1 plus 2 power n cycles to 2 power n plus 1 cycles per conversion. See, the ADC is very slow, so we are sticking to noise shaping SAR ADC, which will complete the conversion in n cycles itself. Now we will go through the SAR ADC working briefly. It basically works on binary search algorithm. It is an iterative method. So n-bit SAR ADC will take n cycles for each conversion. So if we go through the SNR of this SAR ADC, it is dependent on number of bits, which is limited by DAC nonlinearity and comparator offset, and it is dependent on FC, which is the SAR controller frequency. It is limited by the technology, and it is dependent on the input signal frequency. Also it is dependent on K, which is number of cycles per conversion, which is fixed and dependent on number of bits. So decreasing input signal bandwidth is we are not preferring that one. We are trying to reduce number of cycles, thereby we can increase the signal to noise ratio. So, since noise shaping SAR ADC is oversampled ADC, we can look at the sampled sine wave in Nyquist rate case and oversampled case. In oversampled case, the consecutive samples are very close. If we consider an example 10 kilohertz sine sampled at 1 megahertz frequency, the successive samples vary by 62 milli, which is in 8-bit ADC case 16 LSB, basically 4 bits. So, the idea is in SAR ADC, after each conversion, it basically resets to midpoint. So, initial state is in case of 3-bit ADC 1 all zeros in conventional SAR ADC. Instead of resetting after every cycle, we will be continuing from the previous state itself, which is shown in the second figure B. This way, the next output which should be achieved and the current state will be very close to each other. That way, we can converge to the required digital output much faster. So, there is an ADC reported, a variant of SAR ADC, which can do this. It can start the conversion from previous cycle itself, but it takes 2 to 2n plus cycles for each conversion, and this is basically designed in such a way, even it converges faster, the remaining cycles it will stay idle. So, the plan is to eliminate that idle time and start a new sampling clock, so that that way we can increase the speed of the ADC. So, since each sample will take different amount of cycle for converging to required output, the period of each sample will be different. This way, the sampling clock frequency becomes variable. That's why this ADC is non-uniform sampling ADC. So, how exactly this LSB-First SAR ADC works? It works in two different phases, LSB phase. In LSB phase, basically if the comparator logic is 1, it will rise all the bits from LSB side, which are zeros to 1, till there will be transition in the comparator output. That is where LSB phase ends. So, how do we implement this LSB phase? So, to detect these zeros, we will be basically using priority encoder, storing it in the register array 1, which is basically shift register. Using that, after storing in that, using this logic, we will reset the register array 2, which is storing the output. So, that is how LSB phase is implemented. So, it is necessary to detect the transition in the comparator output. So, to detect that, we will be using a transition detector. It is comparator may give a transition from 1 to 0 or 0 to 1. So, two different flip flops are used to detect this thing. T will rise from 0 to 1 on transition. So, that will remain in one state for rest of the conversion cycle. So, to reset it to 0 after every conversion, the D flip flops are controlled by the sampling clock. So, coming to the MSB phase is same as the conventional SAR ADC operation. The only difference is that it won't start from the most significant bit, it will be starting from the bit where LSB phase ended. It is highlighted. So, this is basically how conventional SAR looks. We are trying to reconfigure this architecture using muxes controlled by the signal T, which is transition detector signal. Using that, we will reconfigure in different phases. And coming to the sampling clock generation, so we can see the shift registers at the end of the conversion cycle, the Q0 will be 1. That and the T can be used to generate the sampling clock and sample a new data into the ADC. So, this is the block diagram of non-uniform sampling ADC. sequence of operation goes like this. Initial sample will be triggered forcefully using starter circuits. Remaining samples will be triggered by the control logic for sampling clock generation block. So it's an iterative method similar to SAR ADC. Its difference is that it works in two different phases, and sampling clock is generated automatically. So in LSB-First SAR ADC, as I mentioned earlier, it takes 2n+1 cycles for each conversion. Even if it completes earlier, for remaining cycles it will stay idle. So each sample space will be same in that. So in this implementation, in this work, since we are starting a new cycle after each conversion, the period of conversion for each sample will be different, and it is reduced. We can observe that one. So since the sampling frequency has increased, the consecutive samples difference whatever was there, that will be reduced much further. Thereby the upcoming samples we can converge much faster. So this architecture was tested for controller frequency of 10 megahertz for different input signal frequencies, and with the decrease in the input signal frequency, we can observe the cycles per conversion, the cycles per conversion average cycle per conversion are reducing. It is listed in this table. The average cycle per conversion is going on reducing with the decrease in input signal bandwidth. So we can observe the 31 input signal frequency 3125 hertz case. It is almost average conversion per cycle is 3.5. It is so thus it's more like instead of reducing the input signal frequency by half, we are achieving without doing without reducing input signal bandwidth, frequency. So this ADC was tested for 5 kilohertz input signal and SAR clock of 16 megahertz, for which average cycles per conversion was 3.5 cycles. So the improvement in SNR was calculated. So it came out to be 3.59 dB, and the observed SNR improvement after simulating was 3.5, which is close to the expected value. So this ADC is used as a quantizer in delta sigma modulator to further extend the SNR improvement. As like I mentioned earlier, in delta sigma modulator, the in-band noise will be shaped out, will be attenuated, due to which there will be noise reduction, quantization noise reduction, due to which SNR will improve. So the LS is the loop filter, which is designed by considering average cycle per conversion. So the noise transfer function, which relates output to the quantization noise, is given by this equation. So we can observe its dependence on the T, which is sampling period. In conventional noise shaping SAR ADC case, T is fixed, due to which this will be periodic and we can observe nulls periodically. But in the implementer variable rate architecture, T is variable. So due to which we cannot observe the nulls. After plotting the spectrum, it was evident. The blue one is the conventional noise shaping SAR ADC spectrum, and the other one is variable implemented architecture. Even this was tested for 5 kilohertz input signal frequency, SAR clock of 16 megahertz, and the expected SNR improvement was 10.7 dB, and observed improvement was close to the 8 dB. The this was also tested for second order noise shaping, and the improvement in SNR was expected to be 17.9 dB, and the observed SNR improvement was 16.1 dB. So, since this output need to be reconstructed and decimated, for which decimator need to be designed, but the conventional architecture decimator is conventional decimator is designed for fixed rate ADC. So, the decimator which should be designed for this one cannot be we cannot use the same one. So, that will go down as one of the future work. And also in SAR ADCs, the feedback DAC which will be used is the charge sharing DAC. But since in this one most of the times the MSB bit will be staying idle for the longer time, due to the presence of parasitics, the charge may leak and it may degrade the performance of the ADC, due to which we need to explore whether to stick with the charge sharing DAC or go with the resistive DAC and do the analysis based on that. That will be another future work. So, coming to the conclusion, this work proposes a non-uniform sampling technique to enhance the SNR of ADC. Basically, here we are not decreasing the input signal frequency to increase the SNR. We are sticking to same input signal frequency to achieve a better SNR. The results were noted, and we can observe the improvement in the SNR. Thank you.